Hello and welcome to my C4 Negator and Decoder video of combinational circuits. In this one we're tasked with creating a 4-bit 2's complement negator, and then we're also tasked with creating a 3-input, 8-output active low decoder with an active low enabler. And so we can start with the negator first. So this negator, so it has this control switch that says whether or not we're gonna let it work or not. So no matter what we do here, um, if it basically it's like this will just be the ones comp, or no, it actually doesn't do anything. It just so it just outputs exactly like what the input is. So it doesn't do anything um, if this isn't on, and then if it is on, it'll do the 2's complement. And so this adder here is acting like an incrementer. It's not actually adding two 4-bit binary numbers. It's just saying like whatever this input is, just add one or like do the ones complement and then add one and make it so that's a 2's complement. And so it's basically entirely dependent whether or not this control switch is on. And so say that we wanted to do like, I don't know, what's the 2's complement of say 6. So yeah, what's 2's complement of 6? It'll be that. So it'll be -8 minus, or -8 plus 2, which is -6. And that'll be +6. So there you go. And we can only do like 0 through 7. So we couldn't do like 8. It'll just, because it's negative, it'll just return like 8, I guess, but you can't tell whether or not this is negative or positive. So it doesn't actually do that. It can only really do like these 3 bits here. And then this will be let's see. It'll just act as like the negative or positive like kind of buffer. And just to explain quickly how I got this like adder here, you just go to project, load library, logasim evolution library, and then it'll bring up like, you can find whatever logasim file you would like to take one of your circuits from, and then it'll just like import the folder that it's in, and then you can kind of just drag it in. That way, if you have some sort of useful circuit that's built in a different logasim file, you can import it and then use it rather than having to like remake it again. That helps us save a lot of time. And so let's see here. Oh, and then I got to talk about these XOR circuits real quick. So these XOR circuits are acting as like NOT gates basically, except they only work when this controller is on. So like when this is 0, it doesn't like, when this is 0, it doesn't, these are like all the same. So if this goes in, it'll output 0. If 0 goes in, it'll output 0. If 0 goes in, it'll output 0. But if this is 1, then it flips it. So it acts exactly like a NOT gate, just depending on whether or not our control is on. Which controls not only like the NOT gates, you could call them, but it also controls whether or not we're incrementing the value by 1. So it has like a dual functionality in that regard, which is pretty cool. Let's see, is the adder 4 gate the most efficient way to add 1? I mean, we could have done it with an incrementer. I mean, it doesn't like totally matter. I don't really think it matters that much in terms of like, maybe it uses fewer gates. That's probably it. Probably uses fewer gates. So I'm not like totally sure. But it probably uses fewer gates, which is why I would use an adder rather than an incrementer. It's probably more efficient. Right, and then we can, and then I can just like test the adder, or the negator, so say that, I'll just show kind of how it works. This is our control. And then say that we want to do, I don't know, -4 or something. Turns it into +4. But if we turn this off, it'll just return -4. So it only complements it if this controller is on. And we talk about the decoder. So the decoder, it's this monstrosity, but basically all it's saying is that, and these are all active low, so if it's true, it's going to return 0, basically. So, and so is this. So this is on, even though it's like the opposite, right? So if this encoder, this enabler is off, our thing basically doesn't work. But if it's 0 or if it's low, then it'll work. So say that our input is like 0, because this represents binary numbers, x being most significant and z being least significant bit. Then and our enabler is also quote unquote active. Then it'll return. It'll tell us like what number it is. So say that we just change these to 1, and we say that we don't know how to read binary and say, what is this? Well, it tells us right there, it's 6. Boom, 7. Boom, this is 5. Boom, this is 2. This is 1. So the decoder basically just tells us like which value these bits produce, and this is basically like an on and off switch, the enabler. And this is like we're just testing it. So it does the same thing. Say that we have 7. Boom, it'll do 7. Boom, it'll do 5. Boom, it'll do 1. And then the enabler will change that. So it doesn't really matter what you do. It'll just return 1 for all of them. I mean, and if we wanted to do a larger number of inputs, then I mean, it would depend on how many like bits you had, So if you had I'm pretty sure the 3-bit maximum output, like if you had like a truth table and it had 3 bits, then the most you could get out of that is 8. But if you did 4, then you could do like 15 or something, So depending on your number of input bits, you can pretty much exponentially increase your number of output bits. But your number of input bits would have to scale up at some point, depending on how many number of outputs you would want to have. And then you would just do the same thing. I mean, you would just do all these NAND gates if you wanted active low, and then you would just do like the truth table for all of them, and it would just produce the same thing, except just scaled it to a higher degree. And if we wanted active high outputs, I mean, the enabler would stay the same. If we wanted an active high enabler, then we would just take away this NOT gate here. But if we wanted active high outputs, all we would do is change all these NAND gates to AND gates. And it would do the exact same thing, except it would just be active high. So these would all be 0, and this would be 1, and so on and so forth. And a decoder is useful. So apparently they use them in like computers for, I don't know, say that like there are certain number of tasks that or like, I don't know, say that all of these outputs are connected to I don't know, some CPU. This is an example I heard of. Like, so there's the CPU, and then there are 8 possible functions that I can be running, and say that you want to do only one of these functions, and the CPU can only handle one of these functions at one time. It's like, so you could select whatever binary input, say that it's like the 8th one. It would just and say that you click the button to change these and change it to 8. So say that it was at like 0 and you wanted to change it to, or sorry, not 8, but like 6 or something. Um, no matter how you change it, they all like sort of instantaneously change, so that the CPU only gets one input at once. It just helps with like managing. How do I put it? Like how many things can be active at the same time. I mean, I feel like it's a little bit self-evident, but it's a little bit hard to describe. So I don't know a ton about computers, but that's kind of what I'll explain. Is like it's good for managing like computer like what is active on a computer and what isn't, and managing like memory and storage that way. And yeah, that's pretty much it. I had a little bit of trouble answering some of the questions, but I think hopefully you took something out of it, and appreciate you watching, and thanks for checking out my website. Appreciate it.